Now, Lewis structures provide a model that shows how atoms are arranged and the types of bond that forms, but there are some drawbacks to it. And one of the drawbacks is it doesn't really tell us anything about the molecular shape. So instead, we can use things like molecular models that can help us visualize the 3D shape of a molecule. And they help us see where the atoms would be spatially. So, just kind of as a summary of what I said, right, is that Lewis structures show the atoms and bonds, but not the spatial orientations, right? So when we talk about molecular models, we use these because they can show the orientations and bond angles. And they help us understand the 3D structure. Now, you're going to have a lab where you use models. We're also going to use models in class. But when we talk about this, if you look at the image here, right, we can talk about carbon dioxide as a name, right, or methane as a name. Then we can describe it using a molecular formula, CO2. We can get even more information from the Lewis structure, where it shows us the carbon and then the 2 oxygen atoms here. But with the ball and stick model, we can see here that it's linear. Now, you were probably looking at that and you're like, well, hey, look, I can also see that it's linear here with the Lewis structure. But look at methane. Methane looks really flat as a Lewis structure with only these 90-degree angles. That's what it looks like. But methane doesn't actually have 90-degree angles. Methane's angles are 109.5. And so this is what the structure looks like in 3-dimensional space. Now, I've used this word bond angle, and I've talked about these angles here. And so I want us to talk a little bit more about that, right? So when we refer to the bond angle, this is just the angle in degrees defined by the lines joining the center of 2 atoms, okay? So in reality, what that means is, right, you have a central atom here, okay? And the bond angle is just the distance from one of these atoms to this atom over here, right? So the 2 that are attached to a central atom. Same thing, the bond angle is here, okay? And that bond angle can help describe that 3-dimensional structure for us. And so this leads us to one of the big theories of chemistry, which is valence shell electron pair repulsion theory. That's also known as VESPR. Now, VESPR, what it says is a model. VESPR is just a model that predicts the arrangement of valence electron pairs around a central atom. And this happens in such a way that it minimizes the repulsion of electrons to produce the lowest energy orientation. All that says is that, hey, look, these atoms around this central atom are going to arrange themselves in such a way where they're in the lowest energy. And when they do this, if you've got electrons or bonded atoms, they're going to push away from each other because electrons are negative and they repel each other. That's basically the summary of this. Now, when we talk about VESPR, and really what we're talking about here are the shape of the atoms, we can divide the shape of the atoms into two categories. We have an overarching category, this is the electron domain geometry, and then we have subcategories of that, which is the molecular geometry. So the electron domain geometry is just the 3D arrangement of either bonded electrons, right? Right? And so these are going to be seen as bonded atoms, right? You're going to have a line that shows you the bond and the lone pairs. So you look at all the groups that you could possibly have. So these are all around a central atom. Okay. Now the molecular geometry is just the 3D geometry of the atoms, okay, in a molecule. So let's look at this a little bit. So there are three main types of electron pair geometry that we're going to talk about. There is linear. Now linear generally looks two ways. It can either be two atoms that are attached. So we've got one atom here attached to one atom here. An example of this would be, for example, like F2, right? So we've got fluorine, right? And it makes a linear form. Or what you can have is a central atom and then two other groups that come out from it. If you have this, this would be something like CO2, where you have the carbon in the center and oxygens around like that, and that is a linear molecule. The next molecule that you can have, or the next electron pair geometry that you can have, is trigonal planar. Trigonal planar has a central atom and it's surrounded by three groups or three electron regions. We're going to look at some examples of that on the next slide. And then you can also have tetrahedral, which has a central atom and it has four groups that are surrounding it. And we're going to look at some examples of that on the next slide. So when we talk about electron pair geometries, this can be, right, when you're counting this is bonded atoms and electron pairs, okay? So basically groups, okay? If we look here, and we have, this is CH2O, we've got a central atom here, and we've got 1, 2, 3 groups around it. So those are the three groups. But if we look over here at SO2, they're not showing one of the groups. It's got little lone pairs that sit there. And so we talk about counting those groups to get to this trigonal planar electron pair geometry. There's 1, 2, 3 groups that are associated. So trigonal planar, if it's the electron pair geometry, has 1, 2, 3 groups or 1, 2, 3 groups. That's it. Now, we have to have another word to differentiate between this type of geometry and this type of geometry. And so we use molecular geometry for that. And this is what you're going to focus on in the lab. So when we look at something that is trigonal planar, it has a central atom and 3 bonded atoms to it. If it's bent, right, then when we talk about that, it's got a central atom, 2 bonded atoms, and 1 lone pair, and that is bent. So molecular geometry is a subcategory of electron pair geometry. So let's look at tetrahedral then. When we come down here and we look at tetrahedral, we see that you can have 3 different types of molecular geometries. You can have 4 bonded atoms with no lone pairs. And notice, if there's 4 bonded atoms and no lone pairs, the molecular geometry is the same as the electron pair geometry. They're both tetrahedral. If you have 3 bonded atoms and 1 lone pair, it's now trigonal pyramidal. And so, for example, this is NH3. There's a little lone pair on the top of NH3 there. That is trigonal pyramidal. the reason it's got pyramid in it is because if we look here, that kind of looks like a pyramid, okay? And it's got 1, 2, and then there's a back face, but 3 faces. Then you can have 2 bonded atoms and 2 lone pairs, and if you have that, that's, for example, is like water here, right? And we call that bent, okay? Where we've got 2 bonded atoms here, 1 and 2, and then we've got 2 lone pairs there. So we are going to build some of these in class. You're going to build some in labs. You're going to be able to work on it quite a bit, but I want us to do an example. So we have formaldehyde. It's a gas at room temperature. Aqueous solutions of formaldehyde are used to preserve biological samples. Use VESPR theory to predict the molecular geometry of formaldehyde. So when we think about formaldehyde, it's helpful. The first step here is to draw the Lewis structure. So when you are trying to figure out the molecular geometry, you're going to need to draw the Lewis structure. So when we come here to draw the Lewis structure, right, we need to count the valence electrons that we would have for formaldehyde. So we look and we see that oxygen has 6 valence electrons, carbon has 4 valence electrons, and each hydrogen has 1 valence electron. So we would end up with 12 valence electrons there. We're going to put carbon in the center. Carbon is the least electronegative atom, so it goes in the center. Then oxygen and hydrogen on each side. When we've done that, we've used up 6 electrons. Now, we are going to look here and see if we can put these 6 electrons around the atoms in such a way where oxygen and carbon have a full octet. Remember, hydrogen only needs 1 bond. So we're going to come here and we're going to say, okay, to make oxygen have a full octet, or be surrounded by 8 electrons, there's 2, 4, 6, 8. And so now oxygen has an octet. But the problem here is that carbon does not have an octet. And so we've run out of electrons because we've used our 6 there. So when you run out of electrons like that, what you need to do is form a double bond. So we're going to come here, we're going to erase 2 of these little electrons, right? And instead form a double bond there. And then that now makes carbon happy and oxygen happy as well. Because look, oxygen has 2, 4, 6, 8 valence electrons. So it's got that many electrons that it has access to. Carbon has 2, 4, 6, 8 as well. We can also go back and count as a double check to make sure that our electrons that are used here either in bonds or as lone pairs match this 12. So 2, 4, 6, 8, 10, 12. So this is our Lewis structure of formaldehyde. So that's our first step, right? When you are asked to do VESPR, or when you're asked to find the geometry, that's what you're going to do. That's our very first step there. So when we look at this, right, we see a central atom and it has 3 groups. So the first thing you want to do is identify that electron domain geometry, or the electron geometry. And if it has 3 groups that are attached, whether they're lone pairs or bonds, that's going to end up being trigonal planar. And because that's a central atom and there are no lone pairs on that central atom, and it has 3 other bonded atoms around it, that molecular geometry is also going to be trigonal planar. We're going to continue to work on this in class, as well as talk about polarities, the polar and nonpolar molecules. So we will have an opportunity to practice this quite a bit. So come to class and we will practice this more.